Good afternoon and welcome. This afternoon we conclude this track of CHES with 2 Whitebox sessions with a small break in between. The first Whitebox session is subtitled Whitebox Theory, and the first talk is entitled Whitebox Filtering Attack Breaks SEL Masking from Exponential to Polynomial Time, joint work between Alex Charles and Alexei Udovenko, and Alex will give the talk.
So thank you for the introduction. So I will present you a new class of attack in the Whitebox setting that we call filtering. And when coupled with the LDA attack, it breaks the cell masking scheme in polynomial time. So this is in the Whitebox context. But first, what's the Whitebox context? So as you all know, actually, you all know the black box model, which is basically the usual cryptanalysis against classical schemes. And then from these schemes in which you don't know anything during the computation, you can have some side channel information which we call, in our case, gray box model. And when this side channel information becomes without any noise, we have full information on the implementation, and therefore this model is called the white box model. And in this model, obviously, if the implementation isn't protected, then you can easily recover the key. So we want to protect such implementation from an attacker that has full access to all the information of the algorithm being ciphering. So how we do it? So the main idea of Whitebox will be to protect the key. So how to protect the key? We first choose one that is constant, and we try to embed it inside of the implementation, and such that it would be ideally impossible to retrieve. So to do so, there are 3 families of countermeasures. The first one would be code obfuscation. So we had different talks yesterday about it. And also the first family of countermeasures that was presented and also introduced the Whitebox model is the encoding. And we'll have the next talk will talk more thoroughly about it. And this type of encoding has fallen to the correlation type of attack. And to thwart this kind of attacks, we also can apply masking schemes. So at first, we were applying masking schemes from the side channel research, and but we'll see later that we had to adapt them in order to resist other attacks that this model can bring. So what's the side channel attack in the Whitebox model? So as you are familiar, maybe in the side channel, you'll see that basically we'll have to generate traces also. So how to generate traces? So if you have a function f that takes for input 4 bits and that has for input 4 bits, then you can express this function as you can express this function with bitwise operation. And each of these gates, bitwise gate, we can observe their output. So we call these outputs nodes. And why so? Because we can also consider this representation as a binary tree, but this is not the subject. And so all of these nodes now, what we'll do is, since we have access to the input in the Whitebox, we'll generate a random one. So here in this toy example, 4-bit input. And then we'll record all the value that takes each of the nodes. So doing this and filling in the table one line is called a trace. So we can record multiple traces like this. So if you are more familiar with the side channel family of attack, you can observe here that the traces are actually without any noise, which implies values equal to 0 or 1, because it's software oriented here, so there is no values in between. So, okay, this is for the traces. So alone, it is not necessarily useful. So we need also to have a selection function. So let's suppose that we attack an AES, but we can also attack other algorithms as long as we find another selection function. But okay, for the AES, we know, because we know the AES, we know the structure. So we know that the first byte will be XORed to, the input of the AES is 16 byte, and we'll attack firstly 1 byte of the key instead of the whole key. And this selection function allows to attack 1 byte of the key. So first, we know the input since we are in Whitebox, but we don't know the key, and then we know the AESS box. But since we are attacking only 1 byte of the key, there are only 256 possibilities for the key. And so we can brute force all of these values, basically, and observe the first bit of the output of the AESS box. So, which gives us this value. So for random input, for random traces, we can predict all the values for all the key byte guesses. So now we have both the nodes and the key. So the green part, we have different vectors, and we call them node vectors, and the red part, this is selection function, we call it selection vectors. So why is it useful now? So since in the AES, if we suppose it's a non-protected implementation, there will be at some point in the algorithm a bitwise gate that will output exactly the first bit of the AESS box. So in this case, this means that the gate, that the node, corresponding to this gate will be equal to one of the selection vector. And with enough traces, we can be sure that this is the correct key byte for the key byte that we are attacking. So to avoid such attack, and also and mostly correlation attack that I won't present here, we can apply masking schemes in the Whitebox model. So the first one that was introduced to thwart side channel attacks is the ISW masking scheme. So the name comes from Ishai, Sahai, and Wagner. And the idea of this masking scheme is quite simple. Instead of having bit variables throughout your whole implementation, you'll have instead different shares, here L shares, such that once you are XORing them all together, you retrieve the bit variable that you are trying to hide. And that way, if you are observing for example, x1 here, you cannot observe an equality with one of the selection function. So if we take L equal to 3, so if we take back our example with this masking scheme, instead of having one node equal to one selection vector, one node vector equal to one selection vector, you'll have instead 3 nodes, such that once you are applying the decoding function, so here the XOR, it's equal to one of the key guesses. But how can we find such nodes? So this is where it's very different from the side channel. Since we have values equal to 0 or 1, we can apply algebraic attack. So also I need to say that such attack cannot be run onto the whole set of nodes. So what we'll do is often a sliding window method, so to attack only subset by subsets on the node vectors. So at some point we hope, and otherwise we need to run another window. So at some point we hope that a window will catch all of the shares like this, and which will give us a matrix. So the matrix will have W equal to 5. So this is the window size. So will contain 5 node vectors in this case, and we'll have as many lines as we have traces. On the side, we have still our selection vectors. So how can we now find a combination that the combination of linear, a combination of XORs of node vectors in the matrix such that it's equal to at least one of the selection vector? This is simply solving a linear equation. So we try it for the first selection vector, and maybe we won't find a solution, and we do it for every one of them up until we find a solution. And also it is possible to not find a solution, and therefore this means that one of the linear share at least isn't contained in the window. And then we slide the window and we redo it again. So, so to avoid these attacks, a cell masking scheme has been introduced, and with others too, that also contain a nonlinear decoding function. So here you have the decoding function. Oh yeah, sorry. Cell masking scheme, the name comes from Secker, Eisenbarth, and Liskiewicz. I need to be nice. So this decoding function has a linear part, like for the previous one that avoids exact matching attacks that I quickly presented at the beginning, but also correlation attack. And then XORs a non-linear monomial in the purple part on the right, so of degree D. So this non-linear monomial prevents algebraic attack since it is nonlinear. even if, oh yeah, first an example. So if we have L equal to 2, so 2 linear shares and a degree equal to 2, then we'll have 4 shares in total, such that when we apply the decoding function, we'll have one of the selection vector corresponding to this. So some attacks already exist against cell, but they are all exponential. So most famous ones are HODCA, that is exponential in the parameter L, so the number of green shares, HDDA in the number of nonlinear shares, so the purple ones, and Whitebox LPN, an attack that we proposed last year at CHES, that basically is exponential with this window size, but can be very efficient if D is high. But in the end, they are all exponential, as given here in the complexity. And now I will introduce you a new attack that is polynomial in time here, that has this complexity. So obviously this complexity is incredibly low compared to the others, and also is not dependent on the parameters L and D of cell, which means as long as we have a window and we run the attack, we have a window that contains the shares, and we run FLDA onto it, it will work no matter the degree of cell. So how this attack works? So actually this attack is very simple. So we take the selection function here, and the basic idea is, could we just not nullify one of the nonlinear shares? And if we are doing this, since the nonlinear monomial here is multiplication of shares in the binary field, or if you prefer, end of bit variables, then it will nullify the whole thing, and we'll come back to a linear case. So if we take back our toy example, and let's say that we can, and we want, sorry, to nullify N5. So how can we nullify N5? Actually, it's quite simple. We just choose all of the traces that are equal to 0, that makes N5 equal to 0. And for this subset of traces, then the problem becomes linear. So let's say that we know that N5 is the linear shares, the nonlinear shares to nullify, to filter. Then after, we can also catch everything in the window, nullify N5, filter N5 out, and therefore applying LDA since it's linear. And then at some point, we'll find the correct key. But the problem, obviously, is we don't know which node to nullify. So for this, actually, it's not really a problem. We can just brute force all of them. So we won't go through all of them like this. We'll instead, once receiving a window, we will filter the first column, try to apply LDA after. If it doesn't work, filter the next one and the next one. And obviously, at some point, if the one nonlinear share is contained in the window and all the linear shares are also contained in the window, we'll find a solution. So how much costs such algorithm? So receiving a window M is obviously free. Filtering is linear, so it's negligible compared to the attack. Applying LDA has this complexity with our optimization that I will briefly cover later. And then we are just performing W LDA, so W time LDA, so which gives the final complexity that I've shown previously. So we run our attack over different implementations and also on cell, obviously. And we could recover the key very efficiently. And even for big window size like 400, it's only 5 hours. So it's not, I mean, it's quite fast considering that we don't have any information on the circuit. Oh yeah, to just cover 21% of the nodes since we are attacking the first round. But yeah, but actually it's not very interesting to observe these numbers since the window basically, I mean, what would be more interesting is to observe the time that takes FLDA to process one window. So this we have computed for W equal to 50, and we have compared it to HDDI of degree 2 that we implemented last year. So HDDI of degree 2, to break cell of degree 2, takes 6.5 seconds per window. And while FLDA, for also window size 50, takes only 33 milliseconds. And obviously, since HDDA has a much worse complexity, if we take bigger window or degree 3, it will become, I mean, really incredibly slower compared to FLDA. So filtering actually is a pre-processing method, so it can be applied to every other attacks, side-channel attacks in this setting. So we can indeed nullify a share before applying HUDCA, for example. And what could happen if we do so? We can either filter out a linear share, and therefore we have to run an HUDCA of order 1 less, and or we can filter a nonlinear share and therefore reduce the noise and the number of traces and therefore the complexity of HUDCA. The same can be said for HDA and Whitebox LPN. And filtering adds only a cost of W, as we saw, and a factor of 2 in the trace complexity. Because indeed, since we are filtering out, in average, half of the traces, so if you need T traces to perform your attack, here, in average, you need 2 T traces. So we can also do higher order filtering. So this has no use now, but it is important to know for future designs. So we can also filter multiple nodes vectors at the same time. So just do the binomial, you filter the first column, then try every other one, and then you slide the first column. So this is exponentially cost, but you can also filter multiple nodes at the same time. And also, we brought in the paper, if you're interested, optimizations for LDA. So I've presented previously LDA, and I just shown that you try to solve the linear system for the first selection vector, then the second. This is very slow, actually. What you could do instead is compute the parity check matrix of your window, and multiply it to the matrix containing all the selection vectors. And then it will result in a matrix, and you observe if you have a 0, basically. And this is way more efficient, considering that we have, for DAS, we have to go through 256 times 16 byte of the keys, so it's more efficient. We also brought a new algorithm that we call RNR, so redundant node removal, that is also a pre-processing tool that can be also applied before FLDA and filtering in general, that is only compatible with algebraic attacks. And this algorithm basically is a sliding window that has the same complexity as LDA. And for each of the window, it will reduce it by keeping only the node vectors that are the minimum amount of node vectors that will span the matrix. And therefore, in practice, we halve the number of nodes in the implementation, and therefore multiply by 2 the speed of, let's say, HDGA or FHDGA if you are really fancy. So, and also we brought CPF, so chosen plain text filtering. Since we are in Whitebox, we have access to the input, and therefore we can choose inputs such that the selection function is fixed. And by fixing the selection function, it will fix also the nodes that are related to it, and we can also attack only these parts of the implementation. So to conclude, so cell is not, cell alone, being applied alone, is not safe. So instead, we have now to combine different schemes. So for example, you can apply LDA and a cell, for example, on top of it. But basically, you need to have multiple monomials of degree at least 2 to avoid filtering attacks. But the problem with combining masking schemes is that, okay, cell is, ASW, let's say, is resisting linear attacks, and BU or cell is resisting algebraic attacks. But the combination of the two has no proof that it will resist both. So this raises the need for proofs of combining masking schemes. And also, and as always, a new attack also raises the need of new masking schemes in this setting that will be less heavy and slow, and that will be resisting also algebraic attacks and correlation attacks. So thank you for your attention. You can find our code in our GitHub repository. So yeah, that's it.
Thank you very much. Any questions for Alex? So in your conclusion slide, you suggest to combine things. Do you have an idea what the overhead would be to get a reasonable security level, or is this very hard to predict?
Sorry,
So you propose to combine two masking schemes. So
oh yeah,
it's going to be
we
5
run.
times more expensive or 100 times or is it reasonable?
We run some example. I don't have them in mind, but basically, let's say you have a cost C to transform a set of nodes into another one, then and the cost C2 for the other one, then it will be C times C2, obviously. So this will create a lot of gates, and the more you are applying them on top of each other, the more it will be exponential, basically.
And are there any existing proof techniques that can be reused, or do you have to invent proof techniques from scratch to the security?
So personally, I'm more into attacks for now, that I'm learning now how to do such proofs, so it's difficult for me to answer.
Okay, if there's no more questions, let's thank Alex again for a very clear talk. And so let's move to the second talk in the session. It's entitled On the Impossibility of Preventing Differential Computation Analysis with Internal Encodings. It's joint work between Agathe Ouzelet and Laurent Castelnovi, and Agathe will give the talk.
So hello everyone, and thank you for the introduction. So yeah, I'm going to present you that paper that I wrote together with Laurent Castelnovi. And for those who do not know what differential computation analysis and internal encodings are, of course I'm going to present these notions later. But for now, you only have to know that they are links to the Whitebox model. So everything was already mentioned in the last talk, so I'd be quick here. But contrary to the black box and the gray box models, where the adversary only have a very limited access to the implementation, the white box model defines an adversary who is very powerful, who has a total access to the binary, so he can read and modify it at will, and who also controls the execution environment. And so in this very hostile context, the implementation itself is the last line of defense against key extraction. And by misuse of language, we usually call a white box an implementation of a cryptographic algorithm that is designed to resist an adversary in the white box model. So one of the first questions a white box designer has to think about is how he is going to protect the data in memory. So for instance, imagine you want to perform a XOR between the state and a secret key. Of course, you cannot just store the secret key like that. And so one of the most frequent technique that is used in white box cryptography consists in using lookup tables in order to perform sensitive operations. So instead of storing your secret key, you will store the lookup table. And that's better because it makes some intermediate variables disappear. But of course, this is not enough, since the inputs and the outputs of these lookup table can be highly sensitive. And so what we usually do is that we add encodings that are random bijections applied to the inputs and the outputs of the table. And this is supposed to modify the intermediate variables. So there are two types of encodings. The internal encodings that are supposed to cancel each other during the execution. So the input encoding of an operation is the inverse of the output encoding of the previous one. And then you have the external encodings, so which are the input encoding of the very first operation and the output encoding of the last one. And these encodings are usually set to the identity or cancelled elsewhere. So the encoding techniques was introduced by Cho et al. In 2002, who actually proposed the very first white box implementation of AES. I won't go into the details of this implementation here since it's not needed, but it's just good to know how it works in bird lines, because many designs are based on it nowadays. So you all know that AES is composed of 4 big operations. We have add-run keys, subbytes, shift rows, and mixed columns. So in this implementation, add-run key and subbytes are performed together by a lookup table that takes a state byte as input, decodes it, adds the secret key, puts everything into the S box, and finally encodes it. The shift rows is not very interesting. It's just a shift in the table's inputs. And the mixed column is a bit more complicated, so I won't go into the details here. But just know that it is composed of 2 types of tables. The first type is responsible for the multiplication of a state byte by a constant, and the second type of tables is responsible for the XOR operations. Okay, so unfortunately, after its publication, this white box was broken in several ways. And in particular, if the external encodings are set to the identity, which is usually the case in practice, this white box has proven to be highly sensitive to side channel attacks, as many other designs, in fact. So as you may know, side channel attacks were at first invented for the gray box model, but in 2016, Bart et al. Showed that they could be very well applied to the white box model, and that it gave even more efficient attacks. Indeed, instead of tracing data that is just kind of indirectly linked to the sensitive variable, such as power consumption or electromagnetic emanations, the adversary can directly record the value of intermediate variables or the memory addresses that are accessed during the execution. And doing so, as Alex said, he can obtain just noise-free traces and significantly enhance the efficiency of the attack. So the side channel attack that is going to interest us today is called differential computation analysis, or DCA, and it is the white box equivalent of correlation power analysis, so CPA. And as its a gray box equivalent, it consists in selecting a sensitive variable that only depends on a few key bits, then computing it accordingly to all possible key guesses, and selecting the key hypothesis that gives the highest correlation between the trace points and the computed sensitive variables. So in order to perform this attack, one needs at least the knowledge of the plain text or the ciphertext, so external encodings really prevent it. But this is not really an issue in practice for adversaries, since, as I said, external encodings are often set to the identity in order to respect the standards and for interoperability reasons. So that's it for external encodings, but what about internal encodings? Intuitively, they should hinder the adversary, since they lower the correlation between the sensitive variables and the data that is really manipulated. But it was actually proven that differential computation analysis was very efficient on several internally encoded white boxes. At first, it was really not so well understood, so of course, some authors began to wonder how often does this attack work and why. So in 2019, Rivin and Wang published at CHES analysis and improvement of differential computation attacks against internally encoded white box implementations. And amongst several results, they managed to give the success probability of DCA depending on the size of the random encodings and the number of plain text and of key bits that are involved in the computation of the sensitive variable. Rivin and Wang's work is very generic, so it does not focus only on one cipher or on one size for the encodings, but today we are interested in the protection of the AES, and so in the protection of the S-box output and the mixed columns output, which are the two sensitive variables. And regarding the size of the encodings, we usually want in practice encodings that have a size that is a power of 2, since it is more convenient, and we also want small encodings in order to have not too big memory requirements. So if we resume the work of Rivin and Wang on AES with 8-bit encodings, we obtain something like this. And we see that a DCA targeting an S-box output will succeed with very low probability, while the DCA targeting a mixed columns output will succeed with very high probability, close to 1. And in fact, if we had selected 4-bit encodings instead of 8-bit encodings, these probabilities would be even higher. And even for the protection of the S-box output, like for the attack on the S-box output, we would have a success probability that is quite high. Okay, so this work is very interesting, but it's probabilistic, and in particular, it does not really explain in which cases DCA succeeds or fails. Is it just linked to the encoding, or what happens here? And so in 2016, Sazrich et al. Published another paper that is called White Box Cryptography in the Gray Box, a hardware implementation and its side channels. And in that paper, the authors made several experiments, and they showed that the success of DCA seems to be related to high values in the encoding's Walsh transform. So I won't explain in detail here what's the Walsh transform here. I won't give the formula since it is not needed, but just know that it is a tool that can allow you to measure the correlation between input and output bits of a function. And so in our case, we will use it to measure the correlation between the encoded bits and the plain bits. And so this explains why if you have an encoding that has high values in the Walsh transforms, it means that you have an encoded bit that is highly correlated to one of the plain bits, and so DCA will succeed with high probability. So once again, this work is very interesting. It gives us very good leads, but is mainly experimental, and in particular, they left the construction of secure encodings for future research. So if we resume all we have in the state of the art, we have Rivin and Wang, who managed to compute the success probability of DCA against random encodings, and they showed that it was very high, but not 1. And then we have Sazrich et al., who showed that the success of DCA seems to be linked to high values in the encoding's Walsh transforms. So the questions that we asked ourselves are, does there exist a subclass of encoding that can resist DCA? And so in particular, can we try to carefully craft encodings that have low values in their Walsh transform in order to resist DCA instead of just taking random encodings? So in our paper, we give some answers to these questions, but unfortunately, we realized that they were highly dependent on the targeted operations, and this is why we decided to really focus on AES, and so on the protection of the S-box output and the mixed columns output. And today, because I have to select what I'm going to talk to you about, I'm going to only discuss the protection of the mixed columns output, since in my opinion, this is the most interesting part. But I encourage you to go see the paper if you're interested in what happens for the Xbox output, since it's quite different. Okay, so the idea will be to try to attack the mixed columns output of the first round that is protected by 8-bit encodings having only small values in their Walsh transform. So let us first go to the extreme and see what happened when the encodings only have null Walsh transforms. Usually when one wants to attack the mixed columns output, we have to guess 32 bits of the secret key, which is doable but computationally a bit expensive. And so we decided to perform a chosen plaintext attack and to fix 2 bytes of the plaintext in order to reduce the set of key hypotheses and guess only 2 bytes of the key that I will denote by K1 and K0. And so in the rest of this presentation, I will denote by key star the good key hypothesis and K cross any wrong key hypothesis. And similarly by rho star, the correlation score that is obtained for the good key hypothesis, and by rho cross, the correlation score that is obtained for the wrong key, for any wrong key hypothesis. Okay, so we performed the attack and we obtained something like this. So here on top you have the correlation traces, so the correlation scores for each point of the traces, and on the bottom you have the correlation scores, so it is the highest absolute value for the correlation score for each possible key guess. And in both figures you have the correct key hypothesis that is highlighted in red. So what you can see here is first that a classical DCA obviously won't work since it is looking for the highest correlation. And here for the good key hypothesis, we have a correlation that is equal to 0. By the way, this is totally normal since we chose encodings with null Walsh transform. So the encoded bits are unrelated to the plaintext bits. And yeah, at first sight, what you can see is that this seems to be quite good since the good key hypothesis is not easily distinguishable at first sight. Like, hopefully, fortunately, it is not the only one that leads to a correlation score at 0. In fact, we counted 511 key hypotheses that led to a null correlation. But the thing is that when you compute the probability for a wrong key guess to give you a correlation score that is equal to 0, you find something that is close to 2 to the power of minus 59. So this is quite strange, and we should definitely not have so many hypotheses that led to a correlation score at 0 if it was just random. So something might be off. So we zoomed on the correlation traces that we had on the previous slide, and we saw something like this. And here you can see that there is a clear pattern between the key hypothesis that leads to a 0 correlation score. So something is definitely off. And we realized that for hypotheses of the form K0 cross K1 star or K0 star K1 cross, so that are the hypotheses with 1 correct byte and 1 wrong byte, then the correlation score is always a multiple of one of the encoding's Walsh transforms. But remember that we selected encodings that only have 0 in their Walsh transforms. So this explains why for these hypotheses you have 0 correlations. And unfortunately, it is very easy for an adversary to recover the secret key from the 511 remaining possibilities, since among them 256 will have the same first byte, which will be the correct one, and 256 others will have the same second byte, which will also be the correct one. So yeah, very easy. So we now know that crafting encodings with only null Walsh transforms is definitely not a good idea. So what we could try to do is to try to craft encodings with small non-zero values in their Walsh transform. So that's what we did, and this time we obtained something like this. So again, on top you have the correlation scores, the correlation traces, and on the bottom the maximum absolute value of the correlation scores for each key hypothesis, with the good key hypothesis highlighted in red. So here what you see is that once again the classical DCA won't succeed, because even though the correct key hypothesis is ranked in the first positions, it is not actually first. So yeah, it looks good at first sight. And when you try to understand what happened, you realize that if you select 8-bit encodings, you will always have Walsh transforms that are multiple of 4. And that this will lead to a correlation score for the good key hypothesis that is always a multiple of 1/64. So in fact, if your encoding has a maximum Walsh transform of 4, then the correlation score for the good key hypothesis will be exactly 1/64. If you have a maximum Walsh transform of 8, then the correlation score will be 2/64, and so on. So from there, we computed the probability for a wrong key hypothesis to lead to a correlation score that is greater than 1/64, and we found something that is close to 2 to the power minus 11. So this means that if you select an encoding that has a maximum Walsh transform equal to 4, then each key hypothesis has a probability close to 2 to the minus 11 to have a higher correlation score. And so if you take such an encoding, the key is going to be ranked 34th in average. So yeah, again, in the first one, but not the first. But actually, knowing that, you could maybe recover the totality of the secret key with a brute force attack, but it might be quite computationally expensive. And we have a better idea to do so. So remember that for a hypothesis of the form K0 star K1 cross or K0 cross K1 star, so the hypothesis that have one correct key byte, then the correlation score is always a multiple of the Walsh transform. Okay, so what we could do is to create 256 group of correlation traces that are related to key hypothesis with one fixed key byte. So for instance, the group 0 will correspond to all the correlation traces for the hypothesis 0, 0, 0 ran, 0, 2, etc. until 0FF. And then for the group that corresponds to K0 star, so the good key bit, the good key byte, sorry, you should only have a few possible correlation scores that are in fact the multiples of the encoding's Walsh transforms. And so you should obtain something like this. So here on top we have the correlation traces for a wrong key byte, so you cannot really see anything. And in the bottom you have the correlation traces for the good key byte. So you can see that this is easily distinguishable, and you can easily recover K0 star, and then do the same thing for the other byte and recover the entirety of the key like this. So unfortunately, the conclusion of our work is that no class of small encodings can actually prevent the mixed collisions output, and thus the AES against side channel attacks. I didn't really clearly mention this, but if you take Walsh transforms that are, well, encodings that have a Walsh transform higher than 4, then the classical DCA will succeed just with overwhelming probability, so you can't really do that. And if you craft encodings with only small values in the Walsh transforms, then you might be able to prevent classical DCA, but then we showed that one could adapt the attack in order to break even these specific encodings. Once again, today I only mentioned what happened for the mixed collisions outputs, but I encourage you to see what happened with the S-box outputs if you're interested. It is in the paper. And we also studied what happened with 4-bit encodings, not only 8-bit encodings. Yeah. And so I think that what would now be interesting as a future work is that since we focus on AES, we could try to analyze other operations and maybe see if we can find a crypto system or even build one that could be actually protected with encodings against side channel attacks. And yeah, because I didn't mention it, but for the Xbox output, for example, as was shown by Riva and Wong, 8-bit encodings can definitely be used. So maybe there are some operations there that could help us. And with this is the end of my presentation. Thank you for your attention.
Thank you very much. Any questions? Go ahead.
Thank you for the talk. So I'm not clear what you mean by null Walsh transform, because in my experience, the Walsh spectrum cannot be all zero.
Sorry, by what?
What do you mean by null Walsh transform?
Oh, okay. It's just like, yeah, we try to abstract it because we didn't really want to show the formula for the Walsh transform and everything. But yeah, we're talking about the Walsh spectrum that is reduced to only inputs that have a Hamming weight of 1, because we are really interested in encoded one output encoded bit related to one plain bit. And when we say that we want all the Walsh transform to be equal to 0, it means that the Walsh spectrum should be null. Like, no, yes, there is just 0 in it.
One entries must be 0.
Yeah.
Yeah, okay.
Exactly.
So do you think it's possible to find good encodings which are larger and are still efficient enough?
Well, you could actually protect the mixed Hollands output for the first round, but you would need 32-bit encodings, and in terms of memory, it's just prohibitive.
Any other questions? So if not, let's thank Agathe for a very interesting and clear talk. Thank you very much again.